Gents, welcome back to another video. This is the ultimate grind for BITSAT 2025. This is the question bank series, and today we are discussing the chapter of moving charges and magnetism. So previously we have discussed all the 11 standard chapter and also the few of the 12 standard chapters up till this point. So with this series, our motto is to get stronger in every topic for BITSAT. Okay, and we are doing so by getting stronger in those very important topics from which questions are being asked. So we study the previous year trend and we practice some question based on that. So you get to get a hang of all those important topics for BITSAT. Okay, so that is the motto of this series, to give you the relevant questions for BITSAT just before the exam, so that you can practice on those, build up more questions like those, okay, solve more questions like those, and just boost your score. Okay, that is the motto of this series. So here we have the previous year trends for this chapter. So as you can see, we have questions from Biot-Savart's law, 3 questions from there. Then we have finding B equivalent, so basically application of Biot-Savart's law, and you'll know the formula for a ring and for a wire. So a combination of those can be given, and we'll come to the question. So 11 such type of questions are asked. One of the most favorite topic for BITSAT is to find this magnetic field. Then force on a current carrying wire, 4 questions from there, right? So then we have magnetic moment, 5 questions from there, and finally also questions from magnetic dipole. Okay, so that is the previous year trend. Now we shall practice some questions based on this. With the questions now, so we have question 1. Here we have to find the magnetic field at point O. Okay, so you can see you can break it into 3 parts. One is this wire, okay, both are semi-infinite wires we will make out. Then we have this circular arc, okay, half circular arc, then also this wire, right? So we'll find the magnetic field due to each of this, and we'll see the direction if they add up or they subtract. Okay, so that is how we are supposed to do this question, right? So if you see for the first wire, the point is along its very length, right? And in such a case, the magnetic field becomes 0. Okay, there is no magnetic field along the length of the wire, right? The magnetic field curls around the wire, It's not at the point of the wire, right? So at point O, due to this wire, there is no magnetic field. Now we have this half circular arc, so we can say B1 is 0. Let's come to B2. What happens to B2? So if you see, the direction will be outward. Okay, so outward I can write like this, right? So the direction is outward towards you, since the current is like this. Okay, and what is the magnetic field due to a circular coil? It is mu 0 I upon 2r. Okay, but here if you see, it is a half circular arc, right? So you divide it by half. Okay, so whatever, if you have some theta angle, you can divide it by 360. So in this case it was 180, right? So 180 divided by 360, that is half. Or you can see it is a semicircle, so half divided by. Okay, so mu 0 I upon 4r. So that is the magnetic field, that too in the outward direction. Now B3, so for this wire, okay, it's a semi-infinite wire, as you can see. This point is at a distance of, now this is radius, so this will also be the radius, right, from the center to a point on the circle, okay, or a semicircle. So here this distance is also r, which is the perpendicular distance from the wire, right? That is what we want, because the formula says for a semi-infinite wire we'll have mu 0 I upon 4 pi r. Okay, of course there is sin theta plus sin theta 1 plus sin theta 2. Okay, and for a semi-infinite case, it just becomes 1 becomes 0, 1 becomes 1, right? So 1 is 90, 1 is 90, 1 is 0. Okay, so yeah, so we have this formula. So mu 0 I upon 4 pi r. This is for semi-infinite. If you have an infinite wire, it will be mu 0 I upon 2 pi r. Okay, so you'll see this formula again and again also. Now what is the direction? So you place the thumb in the direction of the field. So you'll get at point O, it is outward, right? At point O, it is outward. Okay, if the point O was over here, it would have been inward. The point O is above, right? So at point O, if you curl it, you'll see it's outward. So both fields are outward. So both of them will add. So the final field will be sum of all these 3. So this and this. So mu 0 I upon 4r and mu 0 I upon 4 pi r. Okay, so it is small r actually. Okay, so mu 0 I upon 4r due to this, and mu 0 I upon 4 pi r. Okay, so option C is correct. So let's come to this question over here. So we have again a circular Okay, circular coil. The magnetic field at the center is B naught. Now you know the formula for B naught. Okay, mu 0 I upon 2R, right? So here it was semicircle, so we halved it, but here it is complete circle, right? Center of a circular coil. So then what is the distance at which the field will become this? Okay, it's what is the distance at a axial point? Okay, so somewhere on this axis, if you have this type of disk carrying a current I, it will produce some field, and if you know the exact formula, it is mu 0 I r square. You are supposed to know this, 2 upon r square plus x square raised to 3 by 2. Okay, you can see if you put x is equal to 0, which is the center of the disk. Now x is axial distance, right? Distance on the axis. So you have a ring, distance on the axis. So if x is 0, the point is basically at the center, right? So if you substitute x is equal to 0, what will happen? So this becomes 0 square and this will get cancelled. R cube cancels with this. You reach over here. Okay, so you can remember this general formula, and you can from there substituting x is equal to 0, you'll reach over here. Okay, now you are asked at what point, so what x will this field become B naught by 8. So substitute over here B naught by 8. Okay, and if you see this part, okay, we'll keep it as it is, mu 0 I upon 2r square plus x square raised to 3 by 2. Okay, now this B naught we know, it is mu 0 I upon 2r, so 1 by 8, mu 0 I upon 2r, and this is I mu 0 I r square upon 2r square plus x square raised to 3 by 2. I can cancel stuff over here, mu 0 I upon mu 0 I can cancel, 2 4s are, right, and again 4 2s are. Okay, so what are we left with? If you see, so we'll have, so here we'll have 8r, and this will take to the other side, so r square plus x square raised to 3 by 2, and 8r that will go on top as this. Okay, we can square on both the sides, so r square plus x square the whole cube, so this is 64 r, we have squared it, so r to the power 4, right? I'm doing some mistake. Okay, this r goes over there, so this becomes r cube, right? So when we square it, it becomes r to the power 6. Okay, you just have to be careful with it. Now take power 1/3, so you'll get rid of this power cube. Okay, and if you see 64 is 4 to the power 3, right? 4 cube is 64. So if we take power 3, 1/3 of the power on both the sides, so 1/3 and 3 will cancel. 64 is 4 to the power 3, and that 1/3 and this 3 will get cancelled, so you'll have 4 r to the power 6 and 1/3, or multiply 1/3 by this, so you'll get r square, right? So 4, you get this equation, it's simple now. X square is 4r square, so 4r square minus r square, so this is 3r square. So r is basically, or x you're supposed to find, x is basically square root of root 3, right? Root 3r. Okay, and we'll only consider the positive case, right? It's of course symmetric, but yeah, so x is root 3r, and that is your correct choice. Okay, simple substitution in the formula, you know both the formulae, and you cancel out and you get to the answer. Okay, of course here you could have expanded and it would have been a mess, but yes, you can always take fractional cube roots on both the sides, and that will make the problem simple. Okay, you're just supposed to see this pattern, right? So that's about these two questions. Over to the next one. Question 3 and 4 over here. In question 3, we are given a particle with a mass m, charge q. Okay, it is moving in a transverse uniform magnetic field. So the magnetic field is perpendicular to the velocity. So suppose the velocity is in the plane, the magnetic field is going inward. So now you are supposed to tell if its initial kinetic energy is t, what will be the kinetic energy after 3 seconds. Some of you might directly know the formula, it's q square b square r square by 2m, is it? Okay, I'm not sure, just check it. You can actually use half m v square, and v you can use r is equal to mv by qb, right? So it is qb by m, right? So q square b square r square, yeah, by 2 and 2m, okay, q square v square r square, yeah, that m square and this m q square v square r square by 2m. Okay, so this is the formula. Okay, and the point is you don't see a t term in this, right? There is no dependence on on time, or rather the better way to understand this is, uh, if you have a particle which is moving with velocity v, magnetic field is like this, right? So what direction is the force? Okay, F is equal to q v cross b. Okay, so q v cross b, so v is in this direction, b is inward, so what direction is the force? V cross b, upward, right? So v cross b, so in the upward direction. So if you see velocity and force are perpendicular, right? So if you see there is no work done, what will be the path of this particular charge particle? So if there is uniform magnetic field over here, the path will be something like this, right? So, circular path, okay, since it is perpendicular to the magnetic field, simple case, right? So if you see, the force is always towards the center of this circle and it is always perpendicular to the velocity, right? So force and velocity are perpendicular, or force and displacement are perpendicular. So displacement is along the tangent and force is along the center, so always perpendicular. So work done is 0, right? Fd cos theta. So F and D are perpendicular, so cos 90 is 0. So work done by the magnetic field on this charge is 0. So work done is 0. Work energy theorem, you know it. Work done is change in kinetic energy. Okay, work done by all the forces is basically change in kinetic energy. Since no work is done, change in kinetic energy is 0. Whatever kinetic energy it initially had, it will also have the same kinetic energy after 3 seconds. Okay, so in the simple case, it won't have, there won't be any change in the kinetic energy. Okay, now here we are given a current carrying wire like this. Okay, I hope it is visible. It is somewhat like this. Okay, this is L, this is also L, but if not mentioned, you are given the function and you might be able to see it through that as well. Okay, this need not be mentioned in the question. Okay, it was good for you, but you can derive it using this, right? You can plug in the value. For instance, a smart way to see this is if you plug in the value of uh, if you plug in L is equal to pi, okay, L is equal to pi, this and this will cancel. So you'll have the sin x function, right? So what this means is, whatever the interval is, pi, it is fitted within the length L. Okay, so if you see length L, what happens to sine between 0 to pi, sin pi is 0, right? Sin 0 is 1, sin pi by 2 is maximum. So if you see, uh, whatever was happening in the length pi is happening in the length L. So the length L is fixed within the length pi. Okay, so that is a smart way to see it. But anyways, you can plug in the values. Okay, you can plug different values for x, like L, L by 2, L by 4. In terms of L you put, so this and this will get cancelled, and you'll get the plot like this. Okay, and if you see, if you plug in x is equal to L, L and L will get cancelled, and sin pi you have, which is 0. If you put x is equal to 0, it's 0. If you put x is equal to 2L, sine of 2 pi, again 0, right? So you can derive it. It's a simple, but this is a smart way of seeing. Okay, but now let's come to the question. What is the force on a wire? It's IL cross B, right? That is how you find force on a current carrying wire. Now remember that if I write it for a small element, so I can write integral, right? So this will be the force. So remember that this dl is nothing but the displacement vector. It's not uh, distance, okay, it's not the length of the wire, it's actually the displacement. Okay, so here the displacement will be from this to this, right, this point with the final initial to final. So you see the displacement is 2l, I and b are constant, so they will come out. So 2i 2il b, right? So that will be the force. Okay, so integration over dl will give you 2l, not pi times something. Okay, it won't be in form of circle. You'll see it is the displacement. Okay, 2ilb, which is option C. Okay, so that was a nice concept behind that question. Over to the next one. Come to question 5 and 6 over here. In question 5 we have 4 particles. neutron, proton, electron and an alpha particle, their paths are shown in a magnetic field which is going in the plane of this paper. Okay, so magnetic field is like this. So you are supposed to tell which among them is the alpha particle. Okay, so first of all we can use F is equal to Q V cross B, and before that also we can see neutron, right? Neutron does not have a charge, it is Q is equal to 0, so QVB, so force is 0, right? So it is pass undeflected from the field. So the particles are coming like this, so the neutron will pass simply like that. Okay, so this is a neutron. Okay, we are supposed to tell about the alpha particle, so this is not it. Now let us see QV cross B. What is the direction of V cross V? V is in this direction coming up, right? All the particles are entering like this, and V cross B. B is inward, right? V is inward, so the force is towards me. So QV cross B is towards me provided Q is positive. Okay, if Q was negative, it would have been like that, and Q is negative for electron, right? So the path of electron will be in that direction because Q V cross B, sorry, V cross B is towards me, right? V cross B towards me, but electron minus Q, so the minus V cross B, so basically outward, right? So here electron, so this is not the answer. So these two are positive charges, as you can see they are proton and alpha particle. Now the question is which among them is alpha. I can simply see it by the logic of this, because if you see alpha particle has a higher charge, right? This will be 2 times q, since velocity and b is same for all, so they enter with the same velocity, so velocity is same, only differentiating factor is q, right? B is same, of course. So only differentiating factor is q. Q for alpha particle is 2 times that of charge particle, sorry, 2 times that of proton, right? So Q is large for alpha particle, so which means that the force is large, right, in case of alpha particle. So it will pull the particle more, right? So it will have a stronger influence and maybe a shorter radius. Okay, that is for us to decide, we'll see. But yeah, so that will have a stronger pull. So this is the alpha particle, it has a stronger pull, right? Stronger deviation from the field. Okay, so it's a sharper radius, and whereas this one has kind of a easy path. Okay, so that is our proton, this should be our alpha particle, and okay, let us decide based on, not based on this, something is going wrong with that logic. So r is equal to mv by qb. Okay, so we'll see which one has the higher radius, since the charge is also mass is also involved in the radius, right? So r is on the basis of force you cannot directly tell. Okay, so r for, let us say, proton, so if you see it is basically proportional to m by q, right? Mass by charge, because v and b are constant. So mass of proton, let us say it is m, this is q, and here for alpha particle it will be m, and this will be 2m and 4k, right? Sorry, 4m and 2k, right? 4 times the mass of the proton and 2 times the charge. So this and this will cancel, m by q cancel. So we have half. Okay, so radius of proton is half the radius, so 2 times radius of proton, or you can simply say radius of for proton will be half that of the alpha particle. So radius of proton is smaller, so this one, right? So this one is the proton, because the radius for it is smaller, right? This radius is smaller. C will have a bigger radius since it has a bigger mass. Okay, so that is also the factor that is contributing. You cannot just say this will pull stronger. Okay, mass is also there. Okay, so yeah, this is the correct logic. So the alpha particle will be this one. Okay, it will deviate like that. Okay, this will have a smaller radius, since its radius of proton will be smaller and radius of alpha particle will be big, which is that C. It is not option C, it is this one. Okay, so they might confuse you with this also, so be careful when you pick the options. So let's come to this one. Here we have a rectangular loop, it has some current I2 flowing through it. As shown, we have a current carrying wire which is kept parallel to this loop. You are supposed to tell what will happen to this loop. Now you know that parallel currents attract, right? If you have two parallel currents, they will have attracting forces on each other. Okay, if you have two anti-parallel currents, they will repel each other, right? This is something that you learn in your NCERT as well. So this will repel. Okay, So now if you see, these two currents are attracting, right? They will attract each other. Okay, so basically you can use Q V cross B also. So Q, the charge is flowing like this in the loop. If you see Q, and this one has B, magnetic field inward. So so B and V. So V cross B, what is happening? So V cross B, okay, V cross B, so that is towards, right? So that logic also you can use. So this is like this, right? They will attract each other. So let's only worry about the loop, since we are asked what will happen to the loop specifically. Now these two currents, if you see, if you use Q V cross B, basically the force on them will not be contributing over here. So we are supposed to see these two loops. Okay, so even in that, if you see, this one is closer, right? So this one will have a higher magnetic field V1. So V1 will be greater than this whatever B2 is, and B2, if you see, it will be opposite, right? This current is in the upward direction, this is in the downward direction, so this will repel in fact. Okay, but this one will be higher, so net will be B1 minus B2. So that will be again in favor of this direction, right? So this direction will have. So what happens to the loop? The loop moves towards the wire, right? So parallel currents attract, of course it will move towards the wire, and this one is far. So of course magnetic field is inversely proportional to R, right? So that this strength will be less. Of course that arm will repel, but this strength effectively it is less. So B1 minus B2 will be still in this direction. So the loop will still move towards the wire. Okay, so that's the answer. Over to the next one. Have question 7 and 8 over here. In question 7 we have two concentric coils which are carrying current presumably, and yeah, of course they have magnetic moment. They are perpendicular to each other. So you can imagine one in this plane and one in this plane like this. Okay, so so you are supposed to tell each one has magnetic moment m or their resultant magnetic moment. Now what is the direction of magnetic moment? So suppose this one is carrying current like this and the other one is carrying current like this. Okay, this will be Ia, right? Magnetic moment is m is equal to Ia, Mia. Okay, so here also m is equal to Ia. Actually we don't need that formula. We can simply say this one is m. So it is in the upward direction, and this one is m, so it is in the outward direction. So one m is in this direction coming towards you, and one is in the upward direction. So they are basically perpendicular to each other, right? One is upward, one is like this. Okay, so they are perpendicular to each other. So what is the formula for adding vectors? m1 square plus m2 square plus 2 m1 m2, so that will also become m square, and cos of the angle between them, so cos of 90, right? So that becomes 0. So m square plus m square, so this term entirely becomes 0. So m square plus m square, 2m square. So basically it's Pythagoras, right? M and m will give you root 2m, not m in m. Okay, so option C is the correct choice over here. So let's come to this one. Here we have two loops. Again, question on magnetic moment. And this one has radius, so they are almost circles. So this one has radius 2a and that one has a. So current is flowing like this. Okay, you can see. So magnetic of dipole moment, again m is equal to Ia, right? And it is a vector, by the way, right? So we are adding it as a vector. Okay, so here there are no signs given, so you are just supposed to focus on the magnetic. Okay, so first one m1. So if we see, due to this loop, it's directly proportional to area, right? So I times, so suppose this is I, so pi a square, right? What is the radius? Pi r square. So radius is 2a and that's square. Okay, so this will be 4 pi a square I. Okay, I into a radius, a is area, pi r square, right? So r is 2a. So you get this. This is m1. Similarly, m2 will be pi a square, right? I into pi a square, right? Because the radius over here is a. Okay, now what will be the directions? If you see, this one will be in the outward direction, that one will be in the inward direction. So this we can write it as negative. Okay, they are in the opposite sense. One is outward, one is inward. Okay, so that's why they have a crossover. Okay, so the question was framed that way. So m1 plus m2 vectorially, or you just add this two, so you'll have 3 pi a square I, right? Vectorially means with the sign. So we have 3 pi square, and of course there is I over here. Okay, it's magnetic moment I, right? So that's about these two questions. Over to the next one. Question 9 and 10, the final two questions for the day. Here we have in question 9 two identical wires AOB and COD. O is the common point, there is one above the another. Okay, COD. Okay, with another O is the common point. The wires carrying current I1 and I2 respectively. Okay, so now point P is lying at a distance D from O, so it is at a distance D from O, and it is perpendicular to the plane containing the two wires. So we have the wires in the plane of the board, in the XY plane, then the point P will be at a distance D from the point, okay? So it's coming out of the plane and it is at a distance. Also it could be going in, but for simplicity let us consider it is coming out of the plane and it is at a certain distance D over from point O, exactly above, right? So now we are supposed to tell what will be the magnetic field at this point. Now you can imagine that the point is over here, suppose the field due to I2, you can see it is going down, right? So if I put my thumb in the direction of the current, so the field at point P will be going down, right? It's going down. So we can say B is equal to I due to I2 upon 2 pi. These are infinite wires, so mu 0 I upon 2 pi r, right? So that is the formula for infinite wire. Is it mentioned in the question? So sometimes but it might not be mentioned. So they might even use the term long, so that also means infinite wire in this case. So here it is in the downward direction, right? Downward y direction. So this is y. So this is x, this is y. So this is in the downward y direction. This point, and V1. Now V1, you feel you to this wire across at this point. Okay, so again put your thumb in the direction of the current, and then if you cross it, if you curl your fingers, you see that the direction is that way, right? That way, so that is positive x direction, right? So I hope you are getting the idea. So this is x, this is y, right? And the point is towards you, z. Okay, so due to this wire, it is minus 1, right, in the downward direction. Due to this wire, it is plus x, right? So this wire, mu 0 I upon 2 pi d is in the plus x direction. So I can, or you can simply see that they are perpendicular to each other, right? This is along x-axis, this is along negative y. So of course they are perpendicular to each other. So you can simply use Pythagoras theorem and answer will be this, right? Magnitude wise, the answer will be this, and direction will be r capital complex, right? So this is basically Pythagoras theorem. So this term is wholly common, so that will come out of the square sign, and you have I1 square plus I2 square raised to the whole square, so raised to half. Okay, so that will be your answer, right? So let's come to this question. This is a nice question. The final question for the day. Here we have particle which is moving with a momentum v. It has charge q, mass m. We'll say okay, and the magnetic field is in a finite region. It's not entirely covered up over the entire space, or it is only in the region D. Okay, with D such that this D is less than P by V. Okay, so this is a very important condition. Do let me know in the comment section what this condition does. Okay, if what will happen if we had the condition other way around? If D was greater than or equal to D by dq. Okay, what will happen in that case? Okay, so do let me know that answer in the comment section. So for now we have D less than dq, okay, for a certain reason. Then the particle is deflected by a certain angle theta by crossing the field. So the particle will enter the field, right? Now the particle enters the field like this, field is inward, 90 degrees between them. So force is upward, right? B cross B, upward. The force will be somewhat like this, and it will make it go in the arc, okay, and it will exit the field, right? So we can connect this field is inward. You can connect this point to the exiting point. That will help in the geometry. Now this exiting angle is given as angle will be measured with the x-axis, so parallel. Right? So x-axis is like this. So this is theta. Okay. So you are supposed to tell the variation of this theta. Now I'll zoom it for you. So the particle is exiting like this. So this is theta, I told you, with the x-axis. Okay. Reflected by an angle theta. Right. So it's deflected. So initially it was going like this, and it's deflected by theta. Okay. So now this will be 90. Right. So this angle will be 90 minus theta. Right. Theta. Then the whole angle is 90 degrees. So this will be 90 minus theta. Now the next thing is I've connected this to this. Right. So this is, you see, this is the radius of the arc, right? That the particle is tracing. So if you see, again this will be 90 degrees, right? This and this, because this is the radius, this is the tangent, right? The radius and tangent are an angle of 90 degrees. So if this is 90 minus theta, this will be theta, right? This is 90 minus theta plus theta. So together it is 90 degrees again. Okay. So now if this is theta, this will be also theta, right? Alternate opposite angles. So these are parallel lines. So this is theta, this is theta, this is theta, this is theta. Okay. So now the question becomes simple. So we played with this geometry because now we have simple, right? Because now you can write sin theta. This is what we want in the question. So sin theta will be the opposite. This is d, right? Opposite upon hypotenuse is r. And this is 90 degrees. So this will be r. So d by r, right? And how to find this r? R is the radius, right? The particle traces out in the magnetic field, which is mv by q, which we have come across in the previous questions as well. Now mv, mass into velocity, is momentum. So everything was given in terms of momentum in this question. So you can substitute. So this will be p and mv by qb. So p by qb. So qb comes on top. Right? So bqd by p. We actually could have done dimensional analysis and ruled out those two options. The correct option is here, bqd by p. Okay, to let you know what that condition does. One hint is that your momentum is mv. So this is mv by dq. Okay, what is that? Do let me know in the comment section. That is almost the hint. Okay, what will happen if the inequality was other here? So that's about today's question. I hope you really enjoy this session and you enjoy the sessions that are coming up for you again on this question bank series. Okay, we'll get stronger in every chapter before BITSAT 2025. Not only in the chapters, but we'll also practice mock tests, which will be coming up soon, maybe the end of this month or in April. Okay, so we'll do the mock test as well. So if you are somebody who wants to join this brand, you are welcome. Okay, this is a perfect channel to start and to hammer it in for your BITSAT 2025. Okay, so I'll see you soon in the next video. Till then, keep enjoying physics.